For more than 2,000 years, people have searched for a city that may have existed only inside one man's story. Every surviving description of Atlantis begins with two dialogues written by the Greek philosopher Plato. Plato said the story reached Greece through Solon, who supposedly heard it from Egyptian priests. But no Egyptian document confirming Atlantis has ever been found, leaving the chain dependent on Plato's own account. Plato placed Atlantis 9,000 years before Solon, far earlier than any known complex city described in his story. His Atlantis was built in rings, circular canals, bridges, harbors, walls, and a monumental center. It was described as wealthy, technologically impressive, and powerful enough to dominate much of the known world. Plato placed Atlantis beyond the Pillars of Heracles, usually identified with the Strait of Gibraltar. That single phrase moved the search from the Mediterranean into the Atlantic, and eventually across the entire world. The investigation begins with a basic question. Was Plato preserving history, reshaping memory, or creating fiction? Before testing locations, the clues must be separated from the mythology built around them later. Plato's dimensions describe an enormous capital and an island larger than many proposed archaeological candidates. The island supposedly held abundant crops, forests, metals, elephants, and a complex network of artificial waterways. Those details imply a large, warm, fertile territory, not merely a small volcanic island. Plato paired the circular capital with a huge engineered plain divided by canals and military districts. Atlantis then attacked the peoples inside the Mediterranean, until an idealized ancient Athens resisted it. This conflict is central to Plato's moral structure: imperial excess against disciplined civic virtue. After moral decline and military defeat, earthquakes and floods destroy Atlantis in a single terrible day and night. Plato even said the vanished island left an impassable shoal of mud that blocked navigation. A real candidate must fit many clues at once, not simply resemble one attractive detail. Plato often used invented stories and idealized societies to explore politics, morality, and human failure. Atlantis fits that pattern. A powerful society becomes corrupt, attacks others, and is destroyed by its own excess. Its story functions perfectly, even if no island matching every detail ever existed. But fiction can still borrow from reality, especially in a region shaped by earthquakes, eruptions, and sudden coastal destruction. That possibility leads to the most famous historical candidate, Thera, now called Santorini. Santorini's circular geography, volcanic destruction, and connection to the Minoans make it visually compelling. Yet a volcanic caldera is not the same thing as a city engineered in concentric canals. The Minoan world was wealthy, maritime, artistic, and deeply connected across the eastern Mediterranean. At Akrotiri, volcanic ash preserved a sophisticated Bronze Age town with architecture, trade, and remarkable art. The site offers something Atlantis hunters crave: an advanced settlement abruptly buried by a natural catastrophe. Around the 2nd millennium BCE, Thera produced one of the most powerful eruptions of the ancient Mediterranean. Ash reached far beyond the island, disrupting landscapes, travel, agriculture, and regional life. Caldera collapse and displaced water may also have generated destructive tsunamis across parts of the Aegean. Coastal infrastructure and fleets could have suffered heavily, weakening trade and communication. But the Minoan civilization did not disappear in a single day. It continued for generations after Thera. Plato's stated date is thousands of years earlier than the Bronze Age world of Thera and the Minoans. The chronology is a major problem for identifying Santorini directly with Plato's Atlantis. Santorini is also far smaller than the territory Plato described, and it lies inside the Mediterranean rather than beyond Gibraltar. The theory works best only if Plato altered the date, location, scale, and political story. Thera may have contributed memories of catastrophe without being the literal Atlantis of Plato's text. If Plato's location is taken literally, the search must move beyond Gibraltar into the Atlantic. One group of theories places Atlantis near the Gulf of Cadiz, where earthquakes, tsunamis, and coastal change are real. Remote images have repeatedly produced shapes that look promising, until archaeology demands stronger evidence. Without inscriptions, datable architecture, and a matching settlement, geometry alone cannot identify Atlantis. Another popular theory points to the Rishat structure in Mauritania because its rings resemble Plato's city. The resemblance is striking, but the structure is a natural eroded dome far inland and vastly larger than a city. Its circles formed through geology and erosion, not through walls and waterways built by an ancient civilization.
The Azores have also attracted theories because they rise above the mid-Atlantic ridge.
But volcanic islands on oceanic crust are not fragments of a vanished continent, comparable to Plato's enormous island. Modern plate tectonics makes a suddenly sunken Atlantic continent geologically implausible. Atlantis is unproven, but real cities and landscapes have disappeared beneath water. In 373 BCE, the Greek city of Helike was destroyed by earthquake and flooding. Helike demonstrates how a real city can vanish quickly through earthquake, subsidence, and water. Pavlopetri preserves an actual prehistoric town beneath the sea, complete with streets and structures. Many ancient coastal landscapes drowned gradually as global sea level rose after the last ice age. These drowned worlds are real, but they usually vanished over centuries or millennia, not a single night. A credible Atlantis discovery would need a complete archaeological context, not a mysterious shape or isolated artifact. Different disasters leave different evidence: erosion, sediment layers, broken structures, subsidence, and datable occupation. The ocean floor is full of patterns that can imitate walls, roads, pyramids, and harbor shapes. Underwater archaeology must distinguish intentional construction from geology, erosion, and modern material. Geology does not prove whether Plato invented Atlantis, but it rules out many literal interpretations. There is no geological space for a recently vanished continent-sized island between Europe, Africa, and the Americas. Modern bathymetry maps the Atlantic floor in enough detail to reject an enormous sunken landmass. Islands can sink gradually as crust cools, erodes, and subsides, but not as intact empires in a single night. Rapid submergence is possible locally, especially during earthquakes, landslides, or volcanic collapse. A volcanic island can lose enormous volume suddenly, creating memories of land destroyed by the sea. Plato may have combined several familiar kinds of catastrophe into one perfected story. That would explain why parts of Atlantis feel historically plausible, while the complete package remains impossible to locate. The story's political and moral precision may matter more than its geographic precision. If Atlantis was designed as philosophy, searching only the seafloor may miss the point of the story. Atlantis did not remain inside Plato's dialogues. Later centuries repeatedly rebuilt it for new purposes. As ancient texts returned to European readers, Atlantis became a geographic puzzle, rather than only a philosophical tale. In the 19th century, writers transformed Atlantis into a lost mother civilization behind Egypt, Mesoamerica, and other cultures. Archaeology does not support the idea that one vanished Atlantic empire created the world's ancient civilizations. Real ancient societies have deep local histories that do not require Atlantis to explain them. Modern esoteric traditions added crystals, advanced energy, psychic powers, and technologies Plato never mentioned. Film, television, novels, and games turned Atlantis into a flexible symbol of lost knowledge. Because the original location is uncertain, Atlantis can be placed almost anywhere imagination needs it. Removing later inventions makes the central problem clearer. Plato is still the only ancient source for the complete story. That does not automatically make Atlantis false, but it sets a very high standard for claiming it has been found. Every proposed Atlantis can now be tested against the same evidence rather than judged by visual resemblance. Santorini fits volcanic disaster and Bronze Age wealth, but fails major chronological and geographic clues. The Gulf of Cadiz fits the western location better, yet no accepted archaeological Atlantis has emerged. The Rishat structure looks extraordinary from above, but its geology and archaeology do not match Plato's city. The Azores satisfy the Atlantic imagination more than the geological and archaeological evidence. Most candidates become convincing only when one clue is emphasized and several others are rewritten or ignored. A strong historical identification should make the evidence converge, not require continuous exceptions. No inscription, city plan, datable archive, or archaeological layer has identified a place as Plato's Atlantis. The absence of proof is not proof that every inspiration was invented, but it limits what can honestly be claimed. The most defensible answer may be that Atlantis is philosophy built from recognizable historical fears, and disasters. The problem is not a shortage of possible locations. It is the ease with which almost any circular or submerged feature can be made to resemble the legend. Near the Bahamas, the Bimini Road has often been promoted as an Atlantean structure, despite strong geological explanations for its formation. Regular shapes can emerge naturally when rock fractures along joints and is later exposed by erosion. Yonaguni's terraces look architectural, but geologists can explain much of the structure through layered sandstone, fractures, and erosion. Archaeologists do not identify cities from shape alone. They look for construction methods, occupation layers, tools, pottery, and organized space. Remote sensing is excellent for finding targets, but shadows, resolution limits, and processing can create persuasive illusions. A genuine discovery must preserve relationships between structures, artifacts, sediments, and time. Dating matters because a spectacular ruin from the wrong century cannot be Plato's Atlantis. The location must also fit the travel routes, polydomentary, political geography, and scale of the original account. An empire powerful enough to challenge the Mediterranean should leave evidence beyond a single later philosophical narrative. When a theory survives only by changing every failed clue, it stops being a testable identification. A useful theory must risk being wrong. Otherwise, every absence becomes hidden proof, and every contradiction becomes part of the mystery. Atlantis survives because it feels both impossible and familiar, a perfect city assembled from real human anxieties. It promises lost knowledge, warns against power, and turns natural disaster into moral judgment. The city vanishes beneath the sea and reappears inside the text that created it. For Plato, Atlantis may have been less a destination than an argument about what societies become. That warning remains understandable, because powerful societies still imagine themselves permanent. The search will continue, because every unexplored coastline and strange formation offers another possibility. But the more evidence-y this is compared, the harder it becomes to defend one literal lost super-civilization. What remains is still extraordinary, a fictional or reshaped city that became more famous than many real ancient places. Atlantis may never be found, because the complete Atlantis may never have existed outside Plato's narrative. Yet the legend preserves real truths about earthquakes, floods, collapsing powers, and the human fear of losing everything. The most important discovery may not be where Atlantis was, but why people keep needing it to be real. Atlantis remains suspended between memory, philosophy, disaster, and desire. That uncertainty is not a weakness of the legend. It is the reason the legend never stops moving. Atlantis may be history, borrowed memory, philosophical fiction, or some mixture we can no longer separate. What we can say with confidence is simpler. The story is real, the search is real, and the city remains unproven. Beyond the pillars, the map still offers room for imagination. But evidence must decide what becomes history. For now, Atlantis belongs where it began, inside Plato's dialogues, and inside the questions they still create.
The lost city remains lost, not beneath a confirmed sea, but somewhere between ancient catastrophe and the power of a perfect story.
For 2,000 years, an impossible machine lay broken beneath the sea, mistaken for little more than corroded debris. Nothing about the object looked like a computer. It looked like a stone fused with green-black bronze. The object came from a Roman-era shipwreck, loaded with art, luxury goods, and scientific knowledge from the Greek world. Greek sponge divers found the wreck by accident around 1900, beginning the first major underwater archaeological recovery. The divers raised statues, pottery, coins, and one fragile mass whose real importance, documentary, remained hidden. Among spectacular sculptures, the small bronze fragments attracted little attention at first. Then a crack revealed something no natural rock should contain: a precisely toothed wheel. The lump was not decoration. It was the remains of an intricate mechanical calculator. A single turn could transmit motion through a network of gears and transform time into positions on the sky. This machine could model astronomical cycles, track calendars, and predict eclipses more than 2,000 years ago. Only about 1/3 of the original mechanism survives, divided today into 82 fragments. The largest fragment preserves the machine's structural core and the most recognizable surviving gear. Understanding it took generations, because corrosion hid the mechanism's internal structure and most of its inscriptions. Early scholars first called it an astrolabe, a navigation instrument, or a mechanical calendar. Later researchers realized the fragments contained a clock-like gear system far more complex than expected. X-rays made the invisible machinery visible, allowing researchers to count teeth and trace gear trains. Modern computed tomography later uncovered thousands of characters that had remained unread for nearly 2 millennia. The inscriptions were not decoration. They described displays, cycles, and instructions for operating the machine.
The original device was housed in a wooden case, with dials and instructions on both sides.
Its power source was simple: a human hand turning a crank. The computation happened mechanically. The gears were bronze, thin, and hand-cut, with triangular teeth rather than modern clock profiles. Every wheel required careful layout, cutting, filing, and fitting, with the tools available in the Hellenistic world. The challenge was not merely making gears. It was fitting many calculations into a compact, layered machine. The surviving fragments suggest a device only about the size of a small box, yet packed with linked cycles. Nested shafts could carry different motions to several pointers sharing the same central display. The front display combined a calendar ring with the zodiac, turning dates into celestial positions. Set the date, turn the crank, and the entire mechanical sky advances together. The front dial displayed the sun and moon against the calendar and zodiac. A small rotating sphere could show the moon's changing phase as its position shifted relative to the sun. The phase display was a mechanical calculation of the changing angle between the sun and moon. But the Moon does not move across the sky at one perfectly constant speed. The mechanism modeled that irregular motion with an ingenious pin and slot system. As the pin moved through the slot, the moon pointer alternately accelerated and decelerated. This translated an ancient theory of the moon's unequal motion into physical bronze. The mechanism also accounted for the slow rotation of the moon's orbital anomaly over several years. On the back, a 5-turn spiral tracked the 19-year metonic cycle. After 19 solar years, the phases of the moon returned to nearly the same calendar dates. The gears converted that long relationship into a repeatable mechanical calendar. Additional cycles refined the calendar, correcting the small mismatch that accumulates over decades. The back of the mechanism carried 2 major spirals, one for the calendar and one for eclipses. The lower spiral tracked the Saros, a cycle that brings similar eclipses back after 223 lunar months. When the pointer reached an inscribed cell, the machine indicated that an eclipse was expected. The inscriptions distinguished solar from lunar eclipses and encoded details about their expected appearance. Tiny notes could describe timing, direction, and other characteristics associated with an eclipse event. A Saros repeats eclipse geometry, but Earth's rotation shifts where the event is visible. A longer exoligmos cycle helped correct the time of day shift across 3 Saros periods. One hand-powered input coordinated calendars, lunar motion, and eclipse cycles across the entire machine. The mechanism compressed decades of astronomical knowledge into a device that could be explored in minutes. Its eclipse mathematics drew on long cycles known from Babylonian astronomical observation. Greek mathematicians transformed those cycles into geometry, ratios, and finally moving machinery. The machine also tracked the 4-year cycle of major Greek athletic festivals. Its inscriptions name festivals including Olympia, Isthmia, Nemea, and Pythia. For its owner, astronomy, calendars, civic life, and sacred festivals belong to one connected system. The covers carried a technical description of the displays, almost like instructions engraved onto the machine itself. The surviving text describes a front display of the ancient Greek cosmos, including the known planets. But the front mechanism is the most damaged part, so its complete design remains debated. Different reconstructions can fit parts of the evidence, especially where gears and pointers are missing. A successful model must match the physical fragments, the tooth counts, the available space, and the inscriptions. Modern teams have proposed compact planetary gearing that recreates the ancient order of the heavens. If the reconstruction is broadly correct, the front was a moving mechanical cosmos. The mechanism reflected the geocentric astronomy of its time, a moving sky organized around Earth. Planetary motion includes apparent reversals, making a complete mechanical display extraordinarily difficult. Ancient Greek models explained these reversals with combinations of circles moving on circles. A gear system could translate those geometrical circles into the motion of a pointer. X-ray readings preserve long cycle numbers, linked by one reconstruction to Venus and Saturn. The known planets were Mercury, Venus, Mars, Jupiter, and Saturn, each with a different repeating pattern. Any planetary system had to fit many motions into extremely limited mechanical space. That is why reconstructions are tested not only mathematically, but mechanically. The parts must actually fit and turn. The surviving evidence supports remarkable sophistication, but some details of the original front remain unresolved. The mechanism is both understood and mysterious. Its core functions are clear, while its complete form is still being rebuilt. The mechanism emerged from a Mediterranean world where astronomy, mathematics, engineering, and trade crossed borders. Who designed it remains uncertain, and several centers or intellectual traditions have been proposed. Its maker combined theoretical astronomy with the practical knowledge of a highly skilled bronze workshop. Every gear ratio encoded a numerical relationship between cycles in the sky. The machine appears to combine Babylonian cycles, Greek geometry, and an Egyptian-style calendar ring. It was not an isolated miracle. It was a synthesis of knowledge accumulated across cultures and centuries. The device may have served teaching, demonstration, calculation, prestige, or several purposes at once. No surviving text tells us exactly who owned it or how often it was used. Its final journey placed it among valuable cargo moving through the late Hellenistic Mediterranean. The ship was probably carrying Greek goods toward wealthy Roman markets when disaster struck. Justing then sense. Statues, pottery, coins, timber, and the mechanism entered a cold, corrosive underwater archive. The wooden housing vanished, bronze plates fractured, and corrosion slowly welded gears into mineral masses.
Most of the original machine disappeared, leaving researchers to reconstruct a complex whole from scattered remnants.
Every modern reconstruction is therefore a negotiation between hard evidence and carefully limited inference. The goal is not to build the most spectacular machine, but the simplest one that explains the evidence. When a model aligns with the fragments, inscriptions, and mechanics, it becomes a testable historical hypothesis. Working replicas let researchers test whether proposed gear trains can move without jamming or contradiction. A successful reconstruction must reproduce the cycles described by the ancient machine.
Today, computer models and physical replicas work together to explore a computer built without electronics.
Nothing else of comparable surviving mechanical complexity appears for many centuries after the Antikythera mechanism. But the gap does not mean ancient engineering vanished completely. Most machines were recycled, decayed, or never preserved. Bronze was valuable, wood rotted, and complex instruments were unlikely to survive by chance. The mechanism survived precisely because a shipwreck removed it from the normal cycle of reuse. It may be the lone survivor of a broader tradition of sophisticated Greek mechanical astronomy. That possibility changes the question from "how was this possible?" to "how much has been lost?" New imaging can still recover details from fragments already studied for more than a century. Each newly read character or tooth count can strengthen one reconstruction and weaken another. The history of the mechanism is also a history of changing scientific interpretation. The machine keeps teaching because its fragments force historians, astronomers, engineers, and classicists to work together. Calling it a computer does not mean it resembled a laptop. It means the device mechanically processed inputs into outputs. A chosen date became a network of calculated astronomical positions and cycle indicators. It belongs to the long history of analog computation, machines that represent quantities through physical motion. The mechanism pushes the history of complex computation much deeper into antiquity. Unlike a static chart, the machine let its user explore changing celestial patterns by turning a handle. It was a manipulable model, an ancient interface for asking, "What happens when?" That makes education a plausible purpose. The machine turned difficult celestial cycles into visible motion. It may also have been a prestige object, demonstrating wealth, learning, and technical mastery. Prediction and calendar planning may have mattered, but the device was probably more than a single-purpose tool. Without its owner, workshop, or complete front display, some questions may never receive a final answer. Yet the surviving machine already reveals an astonishing idea. The sky could be calculated with gears. Inside a portable box, ancient engineers compressed generations of astronomy into bronze motion. Fragments, scans, inscriptions, mathematics, and replicas now work together to reconstruct the lost machine. Turn the crank, and a date becomes a moon phase, a celestial position, and an eclipse prediction. Its complexity was not magic. It was the result of observation, mathematics, craftsmanship, and connected cultures. From 82 fragments, researchers recovered a machine that changed what we thought ancient technology could do. It predicted the sky not by prophecy, but by encoding celestial cycles into ratios of bronze teeth. A small island gave its name to a machine that expanded the known boundaries of the ancient world. The object pulled from the sea was not an impossible computer. It was evidence of a lost mechanical tradition. And inside that corroded fragment, the ancient sky is still waiting to be read. Beneath every ocean, continent, and city, Earth may be storing an astonishing amount of water hundreds of kilometers underground. But this is not a liquid ocean in a cavern. The water is chemically locked inside solid minerals. At these depths, water exists mainly as hydrogen bound into crystal structures, not as free-flowing lakes or seas.
The most important zone lies roughly 410 to 660 kilometers below the surface.
Geologists call it the mantle transition zone, a pressure-built layer between the upper and lower mantle. This hidden reservoir matters because Earth's surface ocean and deep interior are part of one extremely slow water cycle. Water can travel downward with sinking tectonic plates, disappear into minerals, and return through melting and volcanoes. The difficulty is obvious. No drill can reach anywhere close to the transition zone. Scientists investigate this water indirectly, using seismic waves, laboratory pressure experiments, and rare minerals carried upward from depth. Then one tiny diamond inclusion provided the first direct sample from this hidden reservoir. To understand that discovery, first strip Earth into the layers pressure creates beneath our feet. The shallow upper mantle is dominated by olivine, a mineral with relatively limited capacity to store water. As pressure rises with depth, the same chemical ingredients rearrange into denser crystal structures. Near 410 kilometers, olivine transforms into wadsleyite, a mineral that can hold far more water. Wadsleyite does not contain underground droplets. It stores hydrogen inside defects in its crystal lattice. Deeper still, wadsleyite changes into ringwoodite, another high-pressure mineral with major water storage capacity. At about 660 kilometers, ringwoodite breaks down into minerals that generally hold much less water. That sharp drop in storage capacity can force water out and help create tiny amounts of melt. The transition zone may therefore act like a deep sponge, and, at its boundaries, like a water trap. But a mineral's capacity to store water does not prove the entire global layer is filled to that capacity. Because the transition zone is unreachable, scientists read its properties through the way seismic waves travel. Abrupt mineral changes at 410 and 660 kilometers create seismic discontinuities that geophysicists can detect. Seismic tomography converts thousands of travel times into images of faster, slower, colder, and hotter mantle. Their depth, sharpness, and local variations reveal temperature, composition, and possibly the presence of water or melt. Some low-velocity layers near the transition zone boundaries are consistent with small amounts of partial melt. Laboratories test that interpretation by recreating deep earth pressures and temperatures in diamond anvil cells. When hydrous ringwoodite transforms under lower mantle conditions, experiments can produce melt between the new mineral grains.
Seismic observations beneath North America found velocity drops where mantle flow models also predicted downward movement across 660 kilometers.
Together, experiments and seismic data support dehydration melting as one way water may remain trapped near the transition zone. Still, seismic signals and experiments were indirect. Scientists needed a piece of the deep mantle itself. The crucial sample came from a rough diamond recovered near Juína, Brazil. Deep source eruptions had carried the diamond upward fast enough to preserve a mineral formed hundreds of kilometers below. Inside the diamond was a microscopic inclusion, too small to see without specialized instruments. X-ray diffraction identified the inclusion as ringwoodite, the mineral expected in the lower part of the transition zone. It was the first reported terrestrial occurrence of this high-pressure olivine polymine polymorph in a natural sample. Infrared spectroscopy showed that the inclusion was water-rich, in the mineralogical sense. It contained substantial hydroxyl. The preserved inclusion indicated roughly 1 weight% water, locally, within the transition zone mineral. That was direct evidence that at least part of the transition zone is hydrous, not proof that the whole layer is equally wet. The diamond solved one question and sharpened another. How representative was that tiny piece of deep earth? A speck inside a diamond had transformed the debate from pure theory into direct observation. The discovery was widely described as an ocean inside Earth. But that phrase can be deeply misleading. The mineral stores water as hydroxyl, hydrogen bonded within the crystal, not liquid water filling open space. Hydrogen can substitute into defects where metal ions would otherwise occupy the structure. Each grain stores only a small fraction by mass, but the transition zone contains an enormous volume of rock. Across a planetary shell, even 1% water would represent a quantity comparable to vast surface reservoirs. Experiments show wadsleyite and ringwoodite can hold several percent water by weight under suitable conditions. If the entire zone were near saturation, its capacity could equal several surface oceans, but that is a hypothetical upper limit. The real mantle is almost certainly uneven. Wetter near some subduction systems, drier beneath other regions. Where tectonic plates carry hydrated rock deep into the mantle, local transition zone water may become concentrated. Temperature, iron content, mineral chemistry, and mantle flow all change how much water these crystals can hold. Water changes electrical conductivity, seismic speed, strength, and the way mantle rock deforms. Even when hidden inside crystals, hydrogen can make mantle minerals easier to deform over geologic time. That means deep water can influence mantle convection and the long-term movement of tectonic plates. The deep cycle begins when surface water reacts with oceanic crust and becomes stored in hydrated minerals. Sediments, altered crust, and hydrated mantle rocks can transport water toward a subduction zone. As the plate sinks, rising heat and pressure destabilize many water-bearing minerals. Much of that water escapes at shallower depths, helping generate magma beneath volcanic arcs. Volcanoes return part of the subducted water to the surface through magma and gas. But not all water returns immediately. Some hydrated material survives and continues much deeper. Inside the transition zone, wadsleyite and ringwoodite provide new crystal structures capable of storing that hydrogen. The result may be localized reservoirs shaped by ancient slabs, mantle circulation, and mineral reactions. When hydrated material crosses a boundary into minerals with lower storage capacity, water must move somewhere else. Some enters melt, some may migrate upward, and some can be recycled back into the transition zone. This is the deep water cycle, a circulation measured not in days, but in millions of years. Its pace is almost unimaginable, yet over Earth history, it can move enormous quantities between surface and interior. At the base of the transition zone, ringwoodite transforms into bridgemanite and ferropericlase. Because these minerals hold less water, the transformation can trigger dehydration melting. A 2014 study combined high-pressure experiments, seismic imaging, and mantle flow models to test this process. The observed pattern was consistent with partial melt forming where hydrated transition zone material moved downward. Even a very small melt fraction can strongly reduce seismic velocities and change how the boundary appears. If melt rises back upward, dehydration melting could help keep water concentrated inside the transition zone. Together, melting at both boundaries may create a long-lived geochemical filter around the deep reservoir. A similar release may occur when hydrated wadsleyite rises above 410 kilometers into shallower olivine stability. This does not prove a continuous global ocean. It describes mineral-bound water, possible melt, and a highly variable mantle. Every estimate of deep water depends on combining evidence that sees the mantle in a different way. Electrical conductivity can increase when hydrogen is present, but temperature, melt, and composition can produce similar signals. Seismic data also require interpretation. Slow waves may indicate water, melt, documentaries, high temperature, or chemical differences. The mantle is heterogeneous, so one region cannot automatically represent the entire planet. The diamond is direct evidence, but it is still one tiny sample from one locality. Even the diamond's source history depends on models of deep eruption, mantle flow, and mineral preservation. As a result, published estimates of the transition zone's total water content still span a wide range. New deep diamonds, better experiments, and denser seismic networks can gradually narrow that uncertainty. Future maps may reveal whether deep water forms broad reservoirs, narrow slab-fed zones, or a constantly shifting patchwork. The answer will probably be dynamic, because mantle water moves with a planet that never stops convecting. Water weakens mantle minerals, changes viscosity, and can redirect how heat and material circulate. That links deep water to plate tectonics, mantle mixing, and the generation of magma. Water helps rock melt at lower temperatures, making it a powerful ingredient in magma production. Volcanic degassing returns deep water to the atmosphere, where it can eventually rejoin rivers and oceans. Surface water then enters new crust, rides tectonic plates, and begins the journey downward again. The surface ocean is visible and fast-moving. The deep reservoir is hidden and geologically slow. Over billions of years, Grevenst exchange between them may help shape the long-term stability of Earth's water budget. Earth's oceans did not evolve separately from the mantle. The planet's interior has always been part of their history. A planet's mineralogy and deep water cycle may help determine whether water stays at the surface, enters the interior, or escapes. For Earth, the transition zone may be a bottleneck that stores water and controls how easily it crosses into deeper layers. Its mineral phase turns pressure boundaries into valves in the deep water cycle. The story is not an underground sea. It is a planet-sized chemical circulation through solid rock. Its central reservoir lies in the mantle transition zone, between 410 and 660 kilometers deep. Wadsleyite and ringwoodite can store hydrogen in crystal defects at concentrations far above shallow mantle olivine. A diamond from Brazil provided direct proof that at least one part of this zone held substantial water. But one local sample cannot tell us how wet the entire transition zone is. Scientists therefore combine diamonds, seismic waves, conductivity, experiments, and models to estimate the hidden inventory. The minerals may have capacity for several ocean equivalents, while the actual amount remains uncertain and uneven. What is certain is the cycle. Water moves down, changes minerals, and melting, and eventually returns toward the surface.
Even chemically bound water can influence the mechanics of the planet above it.
So the phrase "ocean inside Earth" is useful only if we remember what it really means. One reservoir flows in waves. The other is stored atom by atom inside rock. The next discoveries will come from smaller samples, better instruments, and clearer images of a world we cannot visit. The biggest question remains simple. How much water is actually moving through Earth's hidden mineral reservoir? The answer will reshape how we understand oceans, volcanoes, plate tectonics, and the long-term evolution of the planet. Earth is not hiding a sea beneath our feet. It is hiding water inside the architecture of the planet itself. That line connects rain, oceans, sinking plates, deep minerals, magma, and volcanoes across geological time. The familiar water cycle runs through clouds and rivers. The deeper cycle runs through rocks and tectonic plates. Deep storage can last far longer than any surface reservoir, even though the mantle itself keeps moving. Every journey through the mantle changes the mineral container and therefore changes where the hydrogen can go. That is why pressure, not empty space, creates Earth's hidden water reservoir. The reservoir is invisible because the rock still looks like rock. The water exists in the chemistry. A microscopic inclusion revealed a process operating across a layer thousands of kilometers wide. We know the mantle can hold oceans of water. We still do not know exactly how much it holds today. What lies beneath our feet is not a secret ocean. It is a hidden planetary cycle written into minerals. And that hidden reservoir may be one reason Earth has remained a water world for billions of years. The room is new. The conversation is new. Yet for one impossible second, your brain insists this has happened before. That certainty arrives before evidence. You feel recognition, even while knowing you have never entered this place. Déjà vu can feel physical. A pause, a chill, a tightening attention, as if reality briefly slipped out of sequence. You search for the original memory. A dream, a photograph, another room, but the source refuses to appear. Then the feeling collapses. The room becomes ordinary again, leaving only the question of why it felt so certain. The name comes from French, déjà vu, meaning already seen. But the experience is larger than vision alone. People described strangely familiar moments long before neuroscience gave them a modern name. Different cultures have linked the feeling to dreams, spirits, fate, past lives, or moments repeating across time. Science does not require a hidden timeline. It begins with something more ordinary and more mysterious: memory making an error. The central puzzle is simple. How can the brain produce recognition without retrieving anything documentary that was actually remembered? Memory is not one system. A moment can feel familiar even when you cannot recall where, when, or why. Familiarity is fast and vague. It tells you something has been encountered without reconstructing the encounter itself. You know the face, but not the name. You recognize the street, but cannot remember the visit. Recollection is slower and richer. It rebuilds details, the person, the place, the sequence, and the surrounding story.
In ordinary déjà vu, familiarity surges, while recollection fails to identify a legitimate source.
At the same time, another part of the system knows the present is new. That is what makes the feeling uncanny. Déjà vu is not a full memory replay. Usually there is no precise earlier event you can inspect. It is also different from simply remembering incorrectly. The person often recognizes that the familiarity itself is inappropriate. That awareness may be the key. The eerie sensation could emerge when memory catches its own contradiction. Instead of proving memory is failing completely, déjà vu may reveal that its quality control system is still working. Researchers often look to the medial temporal lobe, a memory network buried deep behind the temples. Structures near the hippocampus help judge familiarity, context, and relationships between parts of an experience.